workshop, Decarb Healthcare. It's let off some steam, decarbonizing humidification and sterilization systems. We have another new format for this workshop, but first I want to tell you that this workshop should be eligible for AIA credits, and therefore we're showing you the AIA logistics. Mercedes is a registered provider with the AIA continuing education systems. So credit earned on completion of this program will be reported to CES records for all AIA members. Certificate of completion for non-AIA members are available upon request, and those certificates may allow you to get other credits for other accreditation processes. It is not meant to include conduct that is commercial in nature, and this is not endorsement by the AA of any material, construction, or other method or manner of handling, using, distributed, or dealing in any material or product. And the presentation is copyrighted. All right, so we have an interesting session for you today. We're going to start off by having a panel discussing our topic, including Jim Crabb, John Rees, and Duncan Curd, and also Austin Barrelin will present a case study. At that point, we're going to go into breakout rooms, and the breakout rooms are going to have a couple of different focuses. So if you imagine that old proverb about the elephant and people are looking at the elephant from different perspectives, we're going to look at the elephant of reducing or eliminating steam in hospitals from some different perspectives. So there'll be an engineering focus, a facility acceptance focus, a design and project focus, and a finance/business case focus. So if you have a preference, we're going to ask that you put that in the chat, and we'll try and accommodate that preference. When we're done in those breakout rooms, we'll finish at about 12 p.m. Pacific. We're actually going to come back together and have an expanded panel discussion, which will include our original panelists, as well as one representative from each group. So each group will choose one person to join the panel. You'll get to present kind of the ideas and the perspective of your room as part of that panel discussion. With no further ado, I'm going to turn it over to Jim Crabb, who's going to talk about a study of reducing steam at a hospital. Jim?
All right, give me just a second to get started here. Sorry. There we go. All right, so what I'm going to talk about here is a new hospital project that we did several years ago that does not use gas at all, for heating at least. But we still had to sterilize and humidify in this building. And we had to make 140-degree hot water for dishwashing. So we did use gas for those purposes. But still, with all that, we got to 148 EUI. So just looking at a traditional hospital design, generally we have multiple boilers that make steam, and that steam might be running at 80 to 100 PSI. We've seen a hospital recently where they were running at 150 for historical reasons, and at any rate, 80 to 100 PSI, and that is equivalent to somewhere around 350, 360 degrees Fahrenheit, the steam that comes out of that boiler. And then what do we do with that steam? There's 4 basic uses for that steam, where we reduce the pressure to make heating hot water, which is generally no hotter than about 180 degrees, sometimes 200 degrees, but somewhere in that neighborhood. So we've taken this 360-degree medium, we've reduced its pressure, and we're using it to make 180-degree water. Then there's domestic hot water, where we, again, reduce the pressure very low, and we're generally making it, most of the water we make is 120 degrees. And then even if we make it hotter and blend it down, we use 140 for dishwashing and sometimes for central sterile. Then we also reduce the pressure way down to make to make low pressure steam to humidify air streams. And then the primary thing that we need this higher pressure steam for is sterilization. And just as an example, boilers tend to be fairly hot. This is an infrared picture of a large water tube boiler, and you can see that it's a large box sitting in the boiler room that is hot. So it's giving off heat 24/7, 365. And in this instance, we're measuring about 145 degrees surface temperature on parts of the boiler. The whole boiler is not that hot, of course. Some areas are hotter, like this handhold here. But it's just sitting there running at a very high temperature, giving off heat, wasting heat. So in the hospital project we're going to talk about, we did a very different approach to heating and cooling the building. We used modular heat pump chillers, where we're using the same machinery to make 44 degree chilled water and 135 degree hot water. And then we have a ground loop out here that basically manages the difference. If we need more cooling than we have available from, if we need to reject more heat than we have a need for, then we reject it to the ground. If we need more heat than we have cooling load, then we can pull it from the ground. And that's, as you can imagine, a fairly intensive process. This particular hospital had, I think, 200 wells, boreholes that were 400 feet deep. And in this case, we were going through solid granite from about 20 feet below the surface on down. That turns out to be pretty good, though, because granite's a very good conductor of heat compared to clay and other soils. But that handled all the heating and cooling, but we still needed a small steam system to do sterilization and humidification. So we use these little modular boilers. Because they're small and modular, they can't really react to the loads fast enough. So we had to create a steam accumulator, which is just a large tank that holds water and maintains the steam pressure and flow out to the system. So in this project, one of the advantages to this approach is that we were able to fit the entire plant into just 4,600 square feet. This is a 100-bed community hospital, full-service hospital that I want to say was about 320,000 square feet, something like that. So relatively small footprint. This stuff right here is the heating and cooling plant. You can see the pumps take up as much space as the heating and cooling equipment. And then we've got the small steam plant as well. So what did that do for us? What I've done here is I've compared the ground source heat pump hospital to another hospital in the same healthcare system, a legacy hospital that has a very nice steam plant that runs at about 80 psi, I believe, and feeds multiple buildings across the campus. Fairly common design from years back that's been carried forward. The EUI of that traditional plant is about 235, whereas our hospital is 148. And if you look here, the blue is the electrical load and the orange is gas. And you can see that generally speaking, our total load is not much greater than the electrical load of the traditional hospital. The big difference, of course, is in gas because, of course, we're only using gas for sterilization and humidification. And I probably didn't show it on that slide, but we do have a booster heater for domestic hot water for the kitchen. So we've gained a lot by doing it this way. And I'll stop there and we'll move to the next.
Awesome. Thank you, Jim. Next, we're going to hear from John Rees and Duncan Curd from Dry Steam, speaking about various ways, alternative ways to humidify in hospitals. John, Duncan, take it away.
See if I can do this. You see my screen?
No, not yet, John.
All right. Think, do you need to allow me to have privileges? Don't,
Hey, John, if it's okay, I'll do. There we go.
okay, very good. All right, let me blow this up. All right, hello everyone. My name is John Reese. I'm a regional manager for dry steam in the Western region. I cover the Western United States and Western Canada. And over the past 5 years, I've worked with a variety of commercial industrial applications, applying humidification in healthcare and other industrial commercial applications. Today, we're just going to take a very quick high-level overview of humidification in hospitals, why we humidify hospitals, how we go about doing that, review best practices for existing systems, and then introduce a new topic, namely high-pressure atomization, in which we'll discuss the next steps and the advantages of it, and the next steps and resources available for that technology. So first, it's important. Sometimes we seem to forget, at least in my experience, that humidification is very important for our hospitals. It's vital for our human health and well-being, especially when we're sick and in need of healing. You know, ASHRAE provides design guidance and standards 170. We have published recommendations as well from the academic task force, and these are all supported by clinical research, of course. Mid-range RH, typically 40 to 60% relative humidity, reduces the viral and bacterial infections, allergic reactions, and chronic respiratory disease. Also promotes human healing by supporting the body's own immune response mechanism. And as well, it provides a very functional, safe, oxygen-rich work environment, such as in ORs, to avoid the possibility of electrostatic discharge and possible explosions. So the bottom line is humidification in hospitals is not discretionary. We must have it. And air hydration is critical for our human health, and it's vital to healthcare's primary mission. How we humidify in hospitals, we do so using isothermal systems. I would say 99.9% of all hospitals use isothermal systems, wherein the significant amount of energy is required to boil water, change state, and introduce hygienic steam to the airstream, utilizing pressurized steam boilers, as well as a variety of types of generators, electric, gas, and steam-to-steam type systems. In the distant past, and more recently, making a new comeback, adiabatic systems, and specifically high pressure atomization, shown here on the right, allow hospitals to provide humidification at a fraction of the energy use by adding water directly to the airstream, thereby raising relative humidity, and as a side benefit, reducing dry bulb temperature, also known as free cooling. So until decarbonization in healthcare becomes a reality, existing isothermal systems are very much a necessity. So it's incumbent on owners and engineers to maximize efficiency wherever possible to reduce energy waste and the carbon footprint as much as possible. Best practices include good quality insulation to reduce condensate loss, recovering hot condensate and taking that back to the boilers and generators where it came from, using state-of-the-art electric and high-efficiency condensing gas generators, which preheat combustion air and make up water to achieve well over 90% thermal efficiency, and water treatment systems to help minimize hard water scaling and efficiency loss for that problem. Now to the subject at hand, adiabatic high pressure systems in hospitals supply RO water, UV treated RO water to inverter driven water lubricated pumps, pressurizing water to 1000 PSI and distributing it through small diameter instrument grade 316 stainless steel tubing for injection to multiple zones, allowing independent RH control in those zones. Atomization, injection, atomization, and evaporation takes place in the wet section of the air handler. And having an increased wet section of at least 2 feet, but 4 feet or more will improve on the evaporation efficiency and reduce water loss. Also note there is no standing water in this system. Everything is pitched to the drain and drains out of the wet section. For hospitals, standard 170, which was just amended its design criteria in 2017 to allow high pressure atomization in hospitals, does require a dedicated UV recirculation loop in the hospitals to eliminate biologic concerns. So advantages of HPA over isothermal systems. Obviously, we're not boiling water, therefore no combustion and no carbon emissions. So that's the primary benefit there. Small fraction of energy use compared to isothermal systems, even combined with the pump, the water treatment systems, and the ancillary devices, it's much less than 10% of the energy use compared to an isothermal system. These systems have very easy maintenance. It's mainly preventative in the water treatment system itself. HPA, high pressure atomization, can satisfy very large loads up to 5,500 pounds per hour and can humidify all occupied spaces in the hospital, and has excellent turn down ratio for the seasonal variable seasonal loads. So up to 90% turn down ratio. One isothermal generator is required for each independent zone that's being supplied humidity, as shown above. Conversely, one HPA can handle multiple zones, multiple independent zones, and each zone can have multiple stage control for fast reaction to changing load conditions. Much of the year, hospitals can take advantage of the free cooling effect provided by HPA and reducing chiller load, energy, and demand by up to 20%, something that isothermal systems cannot provide. Looking to the future, high pressure atomization offers many advantages over traditional isothermal systems. Each state governs local code compliance for hospitals, so it's important to work closely with those local agencies when applying HPA technology. ASHRAE Standard 170 2017 provides general guidelines for applying HPA in hospitals. Consult your local manufacturer representative for any specific applications. We have 3 white papers written on different aspects of adiabatic high pressure atomization technology, and they're available at our website. An emerging technology not discussed today, but worth keeping an eye on, is that of hydrogen fuel to subsidize or replace natural gas entirely. This technology is currently in development in Europe and North America. Dry-Steam looks forward to supporting efforts to decarbonize healthcare and continue to provide healthy humidification in hospitals. Thank you for your time and consideration, and good hydration to you all.
Great. Thank you, John. Now we're going to hear once again from Jim Crabb, who's going to quickly talk about alternative ways to sterilize.
Great. So just a quick overview of how we do sterilization now. Generally speaking, sterilizers are supplied with steam from the central plant, as I showed in that earlier diagram. But there are hospitals, there are situations where there might be standalone electric steam generators. Even some sterilizers have steam generators built in. Generally, that's for smaller applications. The key, though, is that hospitals, anyone who sterilizes instruments, hospitals in this case, are required to follow the manufacturer's instructions for use. And those instructions for use will specify that steam is required in many cases, and it discusses the temperature and the amount of time involved at holding at a certain temperature, and lots of other procedures that our friends in Central Sterile work with every day. And so for right now, and for the foreseeable future, it looks like steam sterilization is here to stay. There are some alternatives. We all know about ethylene oxide having been used for many years. It is pretty rare inside a hospital these days, but it is still used commercially. And then there's a newer technology called hydrogen peroxide vapor that is being used as a low temperature sterilant, taking the place of ethylene oxide. And when I first learned of that, I had hoped that maybe that would be a promising technology that would take the place of steam. But I'm told by some folks I've spoken with at Steris and elsewhere that it does have its place. It's certainly in use now, starting to be used inside hospitals, but steam is here to stay for some time to come. Also, though, steam is used within the central sterile department as to heat the water for disinfection cart washers that need a higher temperature water that make them safe to handle than to put in the sterilizers. Here's a quick list of some alternative technologies. In most cases, those are being used only at the industrial scale. But I have added a link in the chat that shows you some of the alternative technologies that are out there that are being investigated that may one day take the place of steam. But the answer for now is everyone I've spoken to that knows about these things more than I do says steam is going to be around for at least for my lifetime and maybe beyond that. So the hope that I had for removing steam, the need for steam from hospitals is not going away. So we've got to hope that John's correct, that hydrogen gas, either as a supplement or as a substitute, starts to take over. On the other hand, sterilization is about 6% of the average of the total use of the average hospital. So it's a relatively small amount. And if we were left with nothing that we use natural gas for besides sterilization, it wouldn't be all that terrible. So there is hope, but even if we don't move beyond it, it's not using that much. Troy?
Great. Thank you, Jim. Jim just put down the gauntlet or put a challenge out. He said steam is going to be around for a long time. Perhaps we have an opportunity amongst this group to suggest some ways to shorten that half-life. In fact, we're going to do this together. I'm so excited. We heard from 3 great panelists, and we have one other, Austin Barrelin, who is actually going to present a case study. Right, so right now we're going to look at a facility. Austin's going to give some details of that facility, and right after that, we're going to head into breakout rooms. Cassidy already placed in the chat 4 different lenses that you might look at, and we ask you if you have a preference to write in the chat the lens you would like to approach the problem from. You may have more information to make that decision now, and you certainly will after we hear from Austin, who's going to present our case study. Austin?
Thanks, Troy. So I want to preface this case study. It's really going to be a scenario for us to dive into the breakout sessions and I want to lay it out in simple terms here. So there's 6 main uses for steam in a hospital. We've heard a few of them, but I've color coded it here, and we'll see a diagram coming up here that'll make this clear. So we have the first one there, heating. This is reheat or preheat via steam to hot water heat exchangers, also could be used in radiators, but this is steam with a hot water heat exchanger. The red box you see is preheat, using steam coils directly to preheat the supply air. We have sterilization in the central sterile. We have humidification serving the supply air. Domestic hot water through the same steam to hot water heat exchangers, and then as well as cooking, steam kettles or steam ovens, which is less common, but and typically a smaller use. Next slide. And so the temperature at which we need heat in these 6 departments here. For heating, reheat, we need about 160 to 180 degrees. Typically could be less. We don't need steam. Steam is much hotter than that. For preheating, we only need to preheat to 55 degree air, so we don't need much temperature at all there. Sterilization, usually around 300, a little higher than 300 degrees. The only real place you need a high temperature steam or heat in this case. Humidification, again, we only need 212 for that steam humidification. Domestic hot water around 120 to 140, and then cooking, we could do this without steam, but in other ways, and it's relatively minor. So I don't think there's any real temperature requirements here that are going to dictate how we need to design our buildings. And it's worth mentioning that the combustion efficiency is limited by what temperature we have to make the steam. So that's something to take into account here. Next slide, Troy. So we're going to lay out a scenario. This is a hospital. We're going to say it's a large hospital on the West Coast, a little larger than 1 million square feet, so pretty large hospital. And the weather in this area is about 88 degrees average summer high, 26 average winter low, and the peak, it could get down in the 10 and sometimes in the teens as the peak winter low, but we'll just call it 10 to 15 for now. And you'll see a diagram there showing the average highs and lows. And this will affect, keeping in mind that peak winter low of 10 degrees, pretty cold, pretty dry climate. Let's go on to the next slide, Troy. And so our boiler plant here, we have 3 steam boilers, very old, 70 years, 60 years, and 55 years old. And they are 50,000, 40,000, and 30,000 pounds per hour, respectively. This peak heating load is mainly for the outdoor air, so we'll see that difference there. Our winter load, and this particular hospital only runs 1 boiler, even in the winter, and we'll get into that, why they do that. The low temp, that's the outdoor temp. The peak load is about 47%. It's about 25,000 pounds per hour. And that monthly natural gas EUI equates to about 7 to 10 kBTU per square foot. And that's per month. And in the summer, again, only running 1 boiler at roughly half of that peak load that you saw in the winter, about 12,000 pounds per hour. And that we could see that about midnight in July. So, coldest you're going to get in the summer. And monthly natural gas EUI there is 17 to 20. I'm just realizing that's actually switched. So it'll be 17 to 20 in the winter and 7 to 10 in the summer. So let's go on to the next slide. So what are the potential solutions here for getting rid of steam? If you've attended some of our previous workshops, you may know some of these answers. Looking at reheat and steam to hot water heat exchangers. First, we want to reduce the reheat load. That'll simplify our problem, shrink the amount of change we need to make here. And then the remaining heat can be done through heat pumps or hot water boilers. But heat pumps if you're trying to decarbonize here. Preheating, again, very similar. You could do heat recovery to reduce the amount of preheat you need. And then the remaining can be done with a heat pump or hot water boilers. The sterilization, we saw some of those alternative steam methods. I'll say electric steam generators or ethylene oxide are some of the options there that we heard from Jim. Adiabatic humidification as an option to get rid of the steam there for humidification. And by getting rid of steam, I mean getting rid of the central plant steam. And then domestic hot water, we have heat pumps, CO2 heat pumps, which we heard about in the last workshop. Hot water boilers or electric domestic hot water heaters could all be solutions here. And then gas or electric cooktops, which I'm sure all of you have in your house, could be used for cooking there. Okay, so this is a diagram that we will get into in our breakout rooms. I've color coded with the icons there showing the different areas. We have a central plant there in the middle. Those yellow boxes, small yellow boxes, show the boilers. And then the red lines that go throughout the facility are the steam distribution system. You see the main building there at the top, and then you have east and west. That's the main part of the hospital. In this particular hospital, on the bottom, there's a tunnel that goes to these outer buildings, and there is an old laundry there that is out of commission. So what that tells us is that tunnel distribution system was sized for a laundry, which is a lot of steam load, which is no longer needed, but the infrastructure and the steam are still there. And then the only loads that remain in those outer buildings, you have heating hot water radiators and domestic hot water heat exchangers. There's a small sterilization there as well, and some preheat in building A. But the majority of the load is still up in the east and west buildings there. And so we can dive into this a little bit more detail in our breakout session. And next slide, Troy. So some of the things we want to talk about here, the engineering problem, and these are in line with our breakout sessions. The engineering problem, how can these technologies and ideas that we have or that we can come up with solve the steam plant issues? We heard that the steam boilers are 70 years old. That's the clock is ticking on that system, and we're going to need to address replacing that system. So that's the scenario we're dealing with here. We don't want to put in new steam boilers because then we're locking in another 70 years of carbon emissions. So we want to think 70 years into the future. Facility resistance, we want to work with the client and understand why they may be resistant to change and get rid of the steam. It's not an easy thing, especially when there's steam infrastructure throughout the facility. When you have staff that are trained to run the steam system, and putting in new systems creates all kinds of problems and things that you have to handle there. As well as priority in the design process. From a design community and architects and engineers, how do we make these strategies a priority and prevent them from being value engineered out? I think that's something that we have a lot of great ideas that are considered early in the design process, and as you go along and get closer to the end, it's less likely that these ideas can be kept in the design process. And finally, how do we develop a business case to make this attractive from a financial standpoint? How do we handle any financial barriers that come up with switching fuels, switching from gas to electric, or other financial hurdles that we may have? So these are the topics we want to talk about, and I will pass it back to Troy. And you're on mute, Troy.
Thanks, Austin, for setting us up. Just before Cassidy brings us into our breakout rooms, I want to highlight what we're doing. Austin just went over our groups. There's the engineering focus, really digging into the details. facility acceptance focus, right? How do we get folks, the facility managers, the clinicians, and others to accept a change for the type of things our engineering focus room might suggest? You heard some of those from Austin. Number 3, design and project focus. How do we actually get this to happen within our actual design projects? And finally, how do we develop a business case or a finance case to make it happen in real life? This isn't theoretical, y'all. This is an actual facility, and our work in our breakout rooms might help make this transition possible, not just for this group, but for others. So when we get into our breakout rooms, go ahead and introduce yourselves by giving out your name, your job, and then your favorite sandwich. Number 2, take a couple of quick moments to think if there's any ideas that weren't shared here that might help us reduce steam. Jim said for sterilization, we're a long way off. Perhaps you have an idea that can be incubated here that might shorten that development path. Then you're going to dig into the lens focus for your room, for the room that you're in. And finally, if you get done with that, which is unlikely, but if you get done with that, you can take different views of the elephant, choose another lens, and dig into the question of the hour. Let's see if we can solve this case together. When we're done, we're going to come back together at about 3:02 p.m. You're going to choose one person from your room who's going to join our expanded panel, and we're going to have a big discussion about how to solve this problem. Cassidy, take us away. You all had really interesting conversations in your breakout rooms. So we'll just quickly identify who our extended panelists are, and then we'll jump right in. So from our engineering focus room, who's our panelist?
Chris Miller.
Chris Miller, awesome. From facility acceptance focus?
We have Latanya Campbell.
Latanya, excellent. From design and project focus?
We have Steve Gutman.
Steve Gutman. And from finance business case focus, we have Peter Spadia. Great. Well, let's start with our engineering focus. The original panelists are still on the panel, everybody. Engineering, did you guys solve the technical problem here? How are we going to help this facility reduce or eliminate steam? Chris, the question is for you.
You're muted.
Thank you. Basically, we're going to look at our loads and make sure that they can operate, with the reheat coils at lower temperatures. We're going to utilize heat recovery systems to create chill water and produce heat. The one area that we would find to really look at is what's the ultimate load of heating we need, and how do we replace the steam system during the 10-degree months, which may mean that we have to look at other sources such as exhaust air, ground source, to provide heat in that area, and ultimately downsize the steam system. Probably know it can't go completely away, but we have to look at, how to minimize the steam.
Great job, team. So a lot of ideas there. Facility acceptance focus, Latanya, do our facility staff, our clinicians, our administrators going to trust the suggestions that Chris just shared? And how, if not, how are we going to get them to buy in for our case study? How are we going to get the facility mechanic who is really worried about the switch? How are we going to get them enthused about this potential project or change?
Sure. So one of the things that we notice is that hospitals, they're not open to unproven technologies. There's a cultural barrier to that. So we're working towards first identifying things that they wouldn't notice a change. So reducing loads without them noticing any change at all. So those are like the low-hanging fruit. Other things to think about is convincing the staff, the facility staff, that this is helping advance them professionally. So education and training is another thing to think about. then also there's the need possibly implementing something on a more pilot project type of basis in a non-hospital setting, in a more outpatient type setting, some sort of pilot project, some sort of partnership with manufacturers, et cetera. Maybe they'll be more open to something like that. So yeah, so education, smaller pilot projects, looking at low-hanging fruit that they would notice a change. Those are our solutions.
Wow, that's amazing. Curious, engineering group, design project focus group, reactions to what Tanya just shared?
Yeah, we actually talked about some of the same things. I mean, I called them paradigm challenges, but I think cultural barriers is the same idea. And two things that we felt fell into that area. One is cooking. And while I think it was said that cooking is a small, use of steam, if we want to eliminate as much combustion as possible with fossil fuels, cooking needs to be, converted to electricity. And clearly the technology exists. The barrier that we've seen tends to be more of a cultural paradigm barrier. And we talked about the fact that we need chefs to talk to chefs. It'd be like dealing with central sterile issues without talking to the infection control specialist. You'd never do it. So why are we talking about redesigning kitchens without talking to the cooking specialists? So we need to get chefs on board. There's other efforts that are involving professional chefs in helping to change that paradigm, and we need to do the same in the healthcare setting. The other thing that falls into the cultural barrier or paradigm challenge is the design of central sterile departments. And what I mean by that is, I mentioned that sterilizers can come with integral electric steam generators. And so there is a path to using steam for sterilization, but creating that steam with electricity. You feed the sterilizer with high temperature hot water, and you use as little electricity as possible at the sterilizer to convert it to steam. What I understand from talking to manufacturers is the trade-off is the size of the maximum size of the chamber you can handle with an integral steam sterilizer. And forgetting the issues of source water aside, because it does require RO water and special treatment of that water to make it possible to use. But those are things we can solve. But if we have to redesign central sterile with double the number of sterilizers because the chambers are smaller, that obviously has a design ramification that we need architects and equipment planners to solve, because it's all about throughput in a central sterile, and so we need to make sure that we can meet the throughput.
And to add to that, Stephen,
yeah.
the electrical infrastructure of the facility, because
of course, yeah, I mean, all of this is all about is going to impact electrical infrastructure in a huge way, and so that's just the fact of life. If we're going to convert to electricity, we got to deal with electrical infrastructure, and that's different on every site, on every building and every site, and certainly in a retrofit versus new construction. So then we talked about code and regulatory challenges, which primarily relate to humidification. There was some discussion about the fact that ASHRAE 170 has adopted high pressure atomization as an allowable technology, but California code has not. So we're still in a situation where OSHPAD has to be, asked on a case-by-case basis. I think somebody put in the chat.
that was me.
That was you, Chris. Yeah, that you had asked if you could do it at the central air handler. And
yeah, so basically I talked with an official, and he was open to pre-treating the air before it went into the air handler, which, really your outside air load is most of the humidification load.
Of course, and then you're just trimming it for the difference between the zones, right?
With isothermal, yes.
But that's still a case-by-case basis. You have to ask for permission. You have to get the right person on the phone and get them to accept it and go through all that rigmarole. One of the persons on our call, Abdel, who's on the ASHRAE 62.1/170 liaison, said that California is becoming more aligned with ASHRAE 170, and so maybe the future, since ASHRAE 170 is adopted, the future will be that California will adopt HPA as an allowable technology. And then the final are technology challenges, and I think we had some folks from the Energy Commission on our group, and they asked about, are there any technology challenges that need to be addressed? Because the Energy Commission's in a great place to help, fund and promote demonstration projects that demonstrate new technology. And probably the one technology challenge we identified were hydrogen boilers. I don't believe there are any hydrogen fuel boilers installed in the US. And I think I read an article that the first one is installed in Europe recently, in the last several months. So clearly an emerging technology and I'm talking about large boilers, not small residential style boilers, but large commercial boilers. So there's clearly a technology challenge in getting hydrogen fuel boilers, ready for the US market, let alone getting hydrogen distribution and safe handling ready for the American market. So there's clearly a technology challenge there. But combustion is an attractive thing, and green combustion with green hydrogen, if we could figure that out, would solve a lot of problems. So that was our group.
Awesome. Austin, in what time frame do you think the boilers here will need to be replaced?
Sorry, can you ask that again?
Yeah, in what time frame do you think the boilers here will need to be replaced? Like, when will this replacement happen?
I think the boilers are 70 years old, so probably close to their extended expected life. But I'd say you're working with a 10 to 15 year time limit here.
Great. So LaTanya, Stephen, you guys presented some really interesting perspectives on how to think about this and how to gain acceptance, etc. For this facility that we're talking about, this is a challenge, so we're doing this together. But what would your recommendations be for how to move some of the things you talked about forward within the next 10 to 15 years of the extended lifespan?
If you're looking at replacing existing boilers, obviously, sticking with combustion is going to be a much simpler retrofit. And so, those are big boilers to try to, put in hydrogen fuel boilers, but that might be some, if you want to do something that's a demonstration technology and get some, regulatory support from the Energy Commission, maybe there's an opportunity there.
Yeah, I think the challenge in this particular case is we know that there's going to need to be significant investment in this boiler plant over the next 10 years. And so the question is that the right choice? Invest that money in the plant, or how can we move away from that in the course of in that same time period before we have to make major investments in the old way of doing things? Maybe we still end up with a small steam plant, but if we could limit that steam plant to just sterilization, it'd be a radically different plant. And then we could address whether we do it with combustion or with electricity. And that's kind of a question of what the electric grid in the area is doing, right? Some grids are cleaner than others today, and some are heading at a faster pace to decarbonize. Some are starting to think about maybe they should think about that. So that's a challenge. I kind of go back to what LaTanya was talking about, though, with trial projects and how do you get people kind of over that hump. And I will admit that I'm not necessarily the most sympathetic person there because I'm always up for change. But the idea of making some small steps. Try this here. In the case of this particular facility, they've got 30 different places where they could try some different hot water heating technology and try it on a small scale. And if that works, which it will, then take the next step and maybe move toward the next step. And before you know it, it won't be the brand new technology anymore. It'll just be what we do. And in fact, they might start to prefer it over maintaining all that steam system.
And also a case in, just a thought, why even look at, hydrogen powered boilers? Why not hydrogen powered cogen? Then you get your electrical and your steam that you need.
There you go. There you go.
Hey, bringing Peter into the conversation, our finance business case. We've heard lots in this conversation that was beyond how we approached the question in the room, including this. What I'm hearing is this idea of scaling things and kind of building smaller project to next project to gain confidence. And you can imagine ways in which you might fund. You might have a top chef competition in your hospital to fund the change for chefs, right? But with that in mind, Peter, how are we thinking we might pay for some of the improvements that we're looking for here, given the ideas we've heard, as well as the time horizons?
You said it, Troy. I'm going to jump in and answer. You said it. Netflix series, the Great American Hospital Cook-Off.
Great, Steve. You should. That's actually a great idea. I'm not joking. You should trademark that. Excellent. Peter, do you want to share some ideas on the business finance case? And Peter, if you're speaking, you're on mute.
Thank you. Sorry. We were talking about just the age of the equipment and basically how it's difficult to initially start with O&M costs, but in our experience here in California, I assume it's similar in other states. It's pressurized systems, anything above 15 pounds has to be manned 24/7, which has an enormous cost because you're always having an FTE dealing with that. So if you could show cost savings with manpower, savings, so that FTE goes and does something more valuable than watch a boiler, that should make kind of be your first hurdle for case. And then obviously the improvement of the system, operational costs of reducing your overall energy costs, and then if the organization has an internal cost of carbon, that could be a net add, so that you're doing that. And then again, on the West Coast, there's lots of rebates that we have for converting old inefficient systems into new efficient systems. So the idea would be to offset those costs, front costs with hopefully utility rebates. And then with the steam, we agreed that there was really no way of getting rid of the steam for the centralized system, but improving, or I should say not improving, but removing the steam system and converting to hot water would be a, but still centralized hot water delivery system, much like the engineering group was talking about, would have an overall cost savings and with the life cycle cost analysis.
We actually talked both. Some areas are centralized, some areas are decentralized, so it'd be a mixture.
Right.
Well, thank you, panelists. Let's extend our panel even further. So we are all now deputized as members of our extended panel. Let's continue the conversation. Everybody is welcome. I am thinking that the idea of starting kind of with a small demonstration project in the kitchen seems amazing to me. And snowballing really has a lot of implications for how we think about this and how we think about getting support from leadership to make the transition. I'm curious if this idea of Elizabeth called it kind of distributed systems, which is a mega trend in our world right now. I'm wondering what other concepts, the idea of doing this in kind of in a distributed format and including small projects. What does that make you think about potential solutions for getting this particular facility off of steam?
I just had a quick comment that, you know, the Northwest and California are so different. I came from Seattle City Light, and now I'm at UCSF in California, and the problem with the Northwest is fuel switching is not incentivized at all. And so you're basically not going to get incentives for doing a lot of this kind of work in the Northwest because the gas lobby is pretty strong there. So here, these things maybe make more sense, and hopefully we'll take more of the lead on it. But and then one other comment just about the hydrogen. I mean, hydrogen combustion doesn't really sound good to me, but yeah, the fuel cell maybe.
Curious, Latanya or anybody from that group, hydrogen doesn't sound good. That's kind of probably a question for our engineering focus as well. But for facility acceptance, how do we get people to think about new technologies, especially hydrogen, which came up in our group as well as, you know, there's a lot of questions around it. How do we get folks to accept that as we try and move to new paradigms?
Well, I'm not an engineer, but I guess one of the things that we talked about in our group was those legacy technologies that are left over from the past, and the difficulty of upkeeping those type of systems. You know, trying to have staff that understand how to upkeep those things, and or maybe even having to consult with someone outside of your staff because you don't have someone around to do that. So one of the things that we did talk about was making the facilities team understand that new technologies, pushing them towards new technologies, that's advancing their career. That's giving them new professional knowledge, new professional certifications, etc. So education was a key point that we discussed, and how to move the staff forward.
Troy, if I may make a comment on hydrogen, I think specifically for the hydrogen discussion, wouldn't that be outside of the facility conversations? Because we're talking of hydrogen coming and replacing natural gas in pipes that are leading to the site. So it's outside the facility. We were talking that in England, the experiment was where the existing natural gas infrastructure was, they replaced 20% of natural gas with hydrogen, and nobody on the end user side noticed the difference. That is happening in England. When I asked this specific question to our operations and maintenance systems engineering team, they said that they would be concerned with the PG&E infrastructure to be able to deliver safely hydrogen to the facility because of the explosiveness. But then beyond that, within the facility, if pure green natural gas or hydrogen or any other fuel comes through the existing infrastructure, I don't think the facility will object to that, especially if the cost is cheaper than electricity.
Yeah,
maybe I could respond to that here. There is already work going on within North America to look at using enriched natural gas with up to 25% hydrogen content, and with no change or expected change required in hardware. It's really a matter of simply that hydrogen is used to enrich the existing natural gas. So it would come from your natural gas supplier. It wouldn't require any additional infrastructure. At least that's the expectation. And it would be a step towards decarbonizing, or at least obviously reducing the natural gas usage, with an eye to the possibility of moving to an all hydrogen technology at a later stage.
So also with that, I would imagine with the enriched natural gas, it would make fuel cells where it converts natural gas to hydrogen a lot easier to operate.
Mhm.
And, as far as, the real question is between cogen and fuel cell, what is the rebuild cost, and how often, how does the LCCA play into it for both technologies?
I hate to do this. This is just such a robust conversation, and I can see all of you want to keep it going. It is my responsibility to let us know that we are at time, but I offer two options. So firstly, the concept here is that our conversations never need to end. They can continue. They can just move to an asynchronous format. And so I encourage you to go to Decarb Healthcare and continue the conversation. I just put a post in the chat where you can continue. And then the second thing is, frankly, if there's folks who want to stay on and continue this conversation, there's no pressure to do so. But I don't need to end the meeting right away. So our session here on decarb is officially over. But if there's people who want to continue this conversation, I'll leave the meeting open until you are done. Thank you all for joining, for engaging in the way you did in the breakout rooms, and then engaging in the larger panel conversation. I think we learned a whole lot, and frankly made some progress on, for this particular case and in general, reducing steam in hospitals. So great work, everyone, and have a great day.